Welcome to This Explainer. Today, we are absolutely decoding the universe. You know, when a lot of people hear the word chemistry, their minds immediately jump to intimidating math, complex whiteboards, and really complicated lab equipment. But I want to reframe that for you right now. Chemistry, it's simply the shorthand language we use to describe the constant, totally fascinating physical transformations that are happening all around us, every single second of the day. Really, it's the language of change.
Okay, let's dive into this. Think about your own kitchen or garage. What happens when a glass of milk is accidentally left out on the counter during a really hot summer day? Or why does a shiny iron nail left outside slowly turn into a flaky, orange, rusty mess? In both of these everyday situations, the fundamental nature and identity of the initial substance have completely changed. These aren't just unfortunate accidents, they are profound chemical changes happening right in front of your eyes.
To understand this language of change, here is our roadmap for today. 1. The signs of change. 2. The language of chemistry. 3. Types of chemical reactions. And 4. Reactions in everyday life.
All right, Section 1. The signs of change. Spotting a reaction. Before we can write down a chemical equation, we really need to know how to actually identify that a chemical reaction has taken place. I mean, how do we know it's not just a physical change, like ice melting into water? And this brilliantly illustrates exactly what we're talking about. Take a classic experiment, a magnesium ribbon held with tongs and burned using a spirit lamp. When magnesium burns in the air, it reacts with oxygen. But it doesn't just quietly change, it burns with a dazzling, almost blinding bright white flame and turns into a powdery white ash called magnesium oxide. And you can't just unburn that ash to get your shiny metal ribbon back, right? That dramatic change in appearance and material proves a chemical change absolutely occurred.
Now, while a dazzling white flame is a pretty obvious clue, chemists have a highly reliable mental checklist to determine if a chemical reaction is actively happening. There are 4 telltale observations to look out for. A change in state, like a solid turning into a liquid or a gas. A change in color, like our rusting iron nail. The evolution of a gas, which you'd usually see as fizzing or bubbling. And finally, a change in temperature, meaning the reaction gets noticeably hot or cold all on its own. If you see one or more of these, you are quite literally witnessing chemistry in action.
Let's move to Section 2, the language of chemistry, writing equations.
Now that we know how to spot a chemical reaction out in the real world or the lab, how do we actually document it? Let's see how this builds. If we wanted to write down what happened to our magnesium ribbon, we could just write a normal sentence. Or we could write a bulky word equation. Magnesium plus oxygen yields magnesium oxide. But chemists, they love efficiency. I mean, why write all those letters when we have the entire periodic table at our disposal? The sleek chemical formula, Mg plus O2 yields MgO, is just so much faster and way more concise. This shorthand tells us the exact reactants on the left-hand side and the final product on the right-hand side, all separated by an arrow showing the exact direction of the change.
But there is a catch. We always have to obey the law of conservation of mass, which you might remember basically states that matter cannot be created or destroyed. That means the total number of atoms we start with must exactly equal the number of atoms we end up with. Balancing an equation is honestly just like being an accountant, making absolutely sure the ledger balances perfectly on both sides. The steps are beautifully logical. First, draw boxes around each chemical formula. This is crucial. It reminds us never to change the formula itself. Second, list out the number of atoms for each different element. And third, multiply those molecules until the atoms equalize perfectly on both the left and right sides.
Now, what's really interesting about this equation is how clearly it shows that perfect chemical symmetry in action, tracking a reaction between zinc and sulfuric acid. Look across the board, from zinc all the way down to oxygen. The atom count is exactly the same on the left-hand side as it is on the right. Our accountant's ledger is completely balanced, proving for sure that no matter was created or lost during the entire reaction.
To make our shorthand language even more precise and packed with info, chemists add these tiny notations to the end of the chemical formulas. A lowercase g in brackets stands for gaseous, L for liquid, AQ for aqueous, which simply means it's dissolved in water, and S for solid. So, without writing a single full word, a chemist can look at an equation and know exactly what chemicals are interacting, in what quantities, and in what exact physical state. It is just an incredibly elegant system.
Okay, moving right along to Section 3, Types of Chemical Reactions, Categorizing Change.
Now that we know the vocabulary and the grammar of chemistry, what kinds of stories can this language actually tell us?
Well, we can broadly categorize reactions by how the atoms reorganize themselves. The first type is the combination reaction, and this is exactly what it sounds like. Two or more substances combine together to form a single new product. For example, when calcium oxide, also known as quicklime, reacts vigorously with water, they combine to form calcium hydroxide, or slaked lime. What's totally amazing about this specific reaction is that it releases a massive amount of heat. If you were to touch that glass beaker, it would be incredibly hot. When a reaction releases heat like this, we call it an exothermic reaction.
Now, in total contrast to combination, we have decomposition reactions. This is where a single reactant actually breaks down to give simpler products. Usually, this requires some form of energy to force the breakdown to happen. When heating a boiling tube containing lead nitrate over a flame, it forces the substance to break down, and you can visually confirm this chemical change by the emission of those thick brown fumes, which are nitrogen dioxide gas. Because this reaction requires the input of heat to happen, it is known as an endothermic reaction.
Next up, we have the displacement reaction, which I kind of like to think of as a chemical dance where partners get swapped. Imagine iron nails initially dipped into a bright blue copper sulfate solution. After about 20 minutes, the difference is stark. The solution fades drastically, while the nail itself turns brownish. Why does this happen? Well, because iron is more reactive than copper. It literally displaces or kicks out the copper from the sulfate solution, taking its place entirely. That brown coating left on the nail, that's actually the displaced copper.
So the crucial point is understanding our final major category, oxidation and reduction, commonly smashed together and called redox reactions. While the deep, underlying chemistry involves the transfer of electrons, we can simplify this beautifully. If a substance gains oxygen during a reaction, it is oxidized. If it loses oxygen, it is reduced. And the kicker is, these processes always happen together. If one reactant takes the oxygen, the other one must be losing it. It's just a continuous simultaneous exchange of oxygen atoms.
Finally, Section 4, Reactions in Everyday Life, Chemistry Around Us.
So, up to now, we've burned magnesium, we've boiled lead nitrate, and swapped ions in test tubes. But chemistry isn't just confined to a laboratory. Remember those redox reactions we just talked about? Oxidation is a highly impactful natural process that literally surrounds us. One major everyday effect is corrosion. When metals are attacked by moisture and acids in the air, they oxidize. Iron rusts, silver jewelry turns black with tarnish, and copper roofs turn green. This causes massive damage to car bodies, bridges, and ships globally every single year. The other big everyday effect is rancidity. Have you ever smelled old oil or butter? That awful smell and taste is just the fats and oils oxidizing when left exposed to the air.
And this brings us to a fantastic dinner party fact to leave you with. Have you ever wondered why potato chip bags are always so puffy? Manufacturers intentionally flush those bags with nitrogen gas. Nitrogen is mostly unreactive and acts as a shield, completely surrounding the oily chips and preventing them from oxidizing and going rancid before you even open them. Chemistry isn't just trapped in textbooks. It's the invisible architect of our entire reality, from rusting bridges to the crunch of your absolute favorite snack. So the next time you look at the world around you, ask yourself, what invisible chemical reactions are secretly shaping your life right this very second? Thanks for joining me on this explainer, and keep exploring.